Hello world, it's Craig. It's only a guess, but I suspect that many people can point to something in their life that was so captivating that it drew them into a lifelong interest in some particular field or hobby. And for me, this is the design that I can clearly identify as playing a major role in my life and my career and now in my retirement hobby. This is Intel's MCS-85 Minimum System. Well, actually, it's a little modified. It's a minimum system plus one, which I'll get to in a bit. If we go back in time before the 8085, the first microprocessors, the MCS-4 and then the 4040, they were a bit complicated to design around, but, Intel can be forgiven because they were the first microprocessor in the world after all. Then next up came the 8008, and the 8008, I've been doing that in the last couple of videos, and it has all the markings of just a stepping stone development effort that was a placeholder and was almost designed to fail from the beginning. So that takes us up to the 8080, which was a decent processor, and of course the 8080 has the same instruction set as the 8085 almost, but it still required a heroic engineering effort because it had multiple power supplies, complicated clock, higher voltages, and even when the 8080 support chips were available, implementing the 8080 system just was not completely trivial. But then in 1976, Intel came out with 8085, and to emphasize the simplicity of the 8085 based system, Intel started pushing out this MCS-85 minimum system. They sent out engineering boards, and they pushed this as being a legitimate possibility for a single board computer. This minimum system comprised of an 8085 microprocessor. It's got an 8156 static RAM, and that also has I/O and an internal clock or a timer. And then the 8355, which in this case, this is an 8755 EPROM version. So this is a 2K EPROM that also has I/O. Now the 8156 is just the active high chip enable version of the 8155. So more than likely you've seen the 8155 before. This one just has the active high chip enable instead of active low. Using that active high just makes the address decoding on this board a little simpler. So these three ICs, plus a few resistor, a capacitor, and a crystal, created a complete single board computer. And this system simplified computer design to child's play. It had the prospect of giving embedded systems the power of microprocessors, but with the simplicity of a microcontroller without any of the limitations that come with a microcontroller. This is fully expandable. And this minimum system really, really had an impact on me. I very clearly remember seeing this in this 8080, 8085 manual for the first time. Here it is. And thinking, this is a game changer. Now what I've added to this minimum system is an 8185 1K RAM. So this 8156 has 256 bytes of RAM, but that's a little too tight to really have much fun with this. So I added an 8185, which gives us another 1K, so now we have 1.25 kilobytes of RAM. 2 kilobytes of ROM, as I mentioned. There's 38 I/O pins on this. There's a serial port. It's got 4 hardware vectored interrupts, and it's got that hardware timer that's in the 8155. So all of this has absolutely no glue logic. Everything's TTL signal level, and it runs off a single 5-volt power supply. Now, I was in college at the time, so that summer break, when I first saw this, I wire wrapped one of these systems along with a set of MC-1488 and 1489 for the RS-232 drivers, and made a little 3-output linear power supply. And then I spent the entire summer just playing with this hardware, creating software and interfacing it to things. And, not to romanticize it too much, but since I was off to graduate school that fall and then, starting a family and a career and so on and so forth, that was the last summer until I retired of pure, unadulterated freedom to do whatever I wanted to do. Me and this 8085 system, it was my version of the summer of love. Now the 8085, of course, multiplexes its low address byte and bidirectional data on the same 8-pin address data bus. So the low byte of the address is only on the bus for a short period of time, just a few clock ticks. And generally the system needs to latch that low address byte. But key to this system is that the 8156, the 8755, and the 8185 all internally latch that low address byte using the 8085 address latch enable, the ALA, the ALE signal. That means that there's no latches on this board and really nothing to get in the way of implementing a pretty powerful system, at least by standards of the late 1970s. Now the way I'm running this board, I have one of those $8 USB to TTL serial adapters. You know, this kind of thing. This one's a little nicer. This is a D-Tech. But it just goes from USB, and then on this end, it's serial, but it's 5-volt serial. It's not the normal plus or minus 12-volt RS-232. So I have that just connected up on this, and that's actually what I'm using to power the board. And since that's TTL, I don't need a max 232 or plus or minus 12-volt power supplies or the serial driver receiver like the 1488, 1489 that I used in my original board. And then on the other end of this, I'm running the terminal emulator, TerraTerm, on my computer to communicate with the board. And I'll show you what I have so far for a little resident monitor to make this kind of a fun thing to play with. So the I/O is across the top here. There's one for the 8755 and the other for the 8156 I/O ports. And then also you can see there's some little breakout and patch panels here. So if you want to bring a signal like the interrupts or the timer in and timer out to these headers, you can use patches and wire wrap it into the off-board connectors. And I think what I'll do is I'll probably make another little daughter board, a project board that plugs into the back of this, you know, maybe a real-time clock or something, so I can have this sitting on a nightstand. And nice little real-time clock display on this. Not sure what I'll make yet. To make this board useful as a little development or an educational platform or just to play with, I wanted to have a simple resident monitor. So that's what I've been working on lately. Of course, with only 2K of ROM, it's going to be limited, but you've got another 1K of RAM that you can download additional utilities that you need until they start bumping into your code, of course. So this is what I have for the monitor, and I'm still working on it. Now, I wanted to be able to download an Intel hex file directly from my computer to this platform. So I have the accept. If we type in A, it's going to say it's ready. And now I can go get an Intel hex file. I can just say send file. I have one here that's called Hello World Banner. And double click on that to bring it in. It's going to go ahead and send it down. And then each line of that, it puts out a little dot, tells us okay, that all the checksums were okay. And now it has loaded that into memory. The Intel hex file, of course, has already been located in memory, so the destination address is encoded in that file. And for this little program, it was orged at 2800, so the accept command puts the program at 2800 in the data table wherever it was orged at. On this board, the 8755 address starts at 0 and goes up to 7FF, so it first boots off of the 8755, and then the 8156 starts at 1800, and the 8185 starts at 2800 and goes up to 2BFF. So the next command we're going to look at is the dump. And so we can do a dump and we give it an address range. So 2800 and then a delimiter, which in this case is a space, to 2900. We can look at the original program here. It's not completely void of comments, but it's pretty close. You can see all it's going to do is send out a new line and then a little message, the Hello World Craig. It waits for an input, compares that input to the uppercase Q, and if it passes, it sends out the banner and quits. So the next command we're going to look at is the breakpoint. It's got a breakpoint capability. So we do a break, and then what address we want the breakpoint to be, and we're going to put in 280F, which is right at that compare with the uppercase Q. So hit return, and it has set that breakpoint. We know that because we can do a dump again, 2800 to 2810. We can see here that it has changed the original opcode, which was an FE, into E7, which is the restart. So now the program's going to go, it's going to hit that E7, it's going to kick it back out. So let's say go to 2800. It's saying, hello world, it's Craig. It's now waiting for a character input. I'm going to type a 3. And it has returned to the monitor. There's now, we can use the examine register command, X, and we can see all of the registers, including the program counter and the stack pointer. We can see that A has our value, the 3, the 3 is ASCII 3 that we had at the monitor. Now, note that all of these register values are not the actual values at this moment because we're typing commands in here, you know, and it's using the same processor. The processor is servicing our needs right now. But what it has done is before it came back to the monitor, it saved all of the registers, including the program counter and the stack pointer, and it's servicing us. And now when we want to return to our program, so we'll go and we'll run our program, it will restore all of these register values, and that would include any changes we make to it. So right now we can change that A33, we can change that to what it's expecting, which is uppercase Q, which is 5-1. So to do that, let's do a X, but now instead of just examine the registers, we want to change the register. So let's look at A, that's 3-3 now. Let's change that to a 5-1. I'm going to hit the space, and now it's showing us what the next register is. And if we want, we can just skip over these. So that was B, C, D, E, F, or we could change any of these as we wanted, and we just hit return when we're done looking. So now if we do another X, we can see that it has changed that register to F1 or to 5-1. Now when we go, it's going to take off from where the program counter was before, which was 280F. So it's just going to take up. We don't have to use go with an address. We can just say go, and it'll go from wherever the program counter is. So now if we say go, it should see that A is 5-1, and it's going to go ahead and fall through that and display our banner. And so here's the Hello World banner. Now we can go back. We can do a dump at 2800 to 2810, and we can see that since it hit that breakpoint, it took the restart back out and changed that back into the original opcode, which was FE again. All right, so that was the accept, break, dump. We can also fill, so we can fill a memory block. We just say fill 2800, delimiter 2900, and we can give it whatever byte we want to have it filled with. Now if we do a dump, we can see it's filled all of those with A's. Now while I'm thinking about it, it might be handy with if we look at something like the fill command, we do a fill 2800, and then let's say that we mess this address up. We type it 26 and we say, oh, that's not what I wanted. I wanted 2900. You can just keep typing, and since it's expecting 4 digits here, it's only going to keep the last 4 digits. So you can just type whatever you want, and as long as you catch your mistake before you put the delimiter in, it'll go ahead and accept it. So it's going to take all of that 265, 2900, and it flushed everything out except for the last 4 characters. So we put the delimiter in, and then we can give it the value, and it'll do the same thing on that 55. It would have just kept, it would have flushed anything except for the last 2. Okay, so we can see those are all 55s. All right, we can either do a H for help or a question mark, and either of those will pull up the command list. And it's kind of abbreviated here, and it might get more abbreviated as I really get desperate for room. Let's look at the insert and the substitute command. They're both related, and they're both ways to get data in. Insert lets you just type a bunch of hex values. So I can say I2800, hit the enter key, and now I can just 1 2 2 3 4 5 5 6 so forth. Let me hit the escape to get out of that. Dump 2800 to 2810, and we can see our values there: 1 2 2 3 4 5 5 6. Now substitute does the same thing. It's still just going to put into memory, but let me do substitute 2800. With substitute, it actually hit the space key. It's going to show us what's in memory now, and if I want, I can change it by just entering a new value. If I don't want to change it, I can just hit the space bar, and it'll skip over to the next address. So that's the difference between substitute and memory. I'm sorry, that's the difference between substitute and insert. Insert, you just type hex values. Substitute, it shows you what it is, and then you type it. Substitute just requires one more keystroke because you're going to hit that space bar between each one of them. All right, and then there is the move command. I've since renamed that to copy, but it just copies code. You give it the source, you give it the end, and then the destination, the starting address, and it will copy command. So we can say move from 0000 to 03FF to 2800. And this is actually the monitor that we're looking at here. So this is the first block of the monitor. Now, this is not translating anything. It's not changing your jumps or any code references. It's not translating this. It's just simply copying. So that's it so far. I think we've looked at all the commands. Yep, that's it so far. So what I've got going, but what I would really like to fit in this is a disassembler. And even if I have to throw out some other commands, like I don't use the substitute, or I don't use the insert at all anymore now that I've written the accept command. So even if I have to throw out the insert and the substitute, maybe the fill and the move, I would really like to have a disassembler. This monitor is still it's still a work in progress. Now I should point out that I lifted heavily from Intel's SDK-85 resident monitor, which Intel lifted from the SDK-80 monitor. So if you're familiar with using either of those platforms, this monitor will feel natural to you. The go, the insert, substitute, examine, those commands are all lifted directly or pretty much from the SDKs. The accept Intel hex, the breakpoint, and the dump are mine, and the disassembler that I'm trying to get to fit, I'm planning on lifting as much of that from the Millman 80 monitor as I can. So right now where I have is I've got my assembly code and I have a bunch of conditional assemble statements in it here, and I'm taking things out, putting them in, working on the assembler, and trying to see what I can fit in there at the same time. So let me know what you see as priorities for this 2K resident monitor and what can be pushed off as a utility that you load in RAM when you need it. Be interesting to see what weight other people put on some of these commands. The other thing that I hadn't mentioned is a single step. I would like to have a single step in here, and I'm not sure if it's worth expanding the break table so that I can have a full break table. I know that only a few people, if any, I suppose, will have a keen interest in this board. I imagine the MCS-85 minimum system, probably just doesn't spark as much joy to nearly anybody else as it does me. Furthermore, and probably more importantly, I suspect that most people can't program the 8755. And that's probably the more severe limiting factor. But, really that shouldn't even be a showstopper if you're really interested in this platform, because there is an easy solution for this. Now, to back up a bit, the 8755 programs almost identically to the MCS-48 family, so the 8048. And Intel recognized that, and you would basically, back in the day, just use an adapter card and program the 8755 on a MCS-48 programmer. So I was searching the internet to see what options people might have to program this little guy, and I came across somebody who has designed an MCS-48 programming shield for the Arduino. And he has shared the design and software on his website. And I'll put a link to his project below. It's just mattmillman.com. Or if you search for MCS-48 programmer or 8755 programmer, his site will be very near the top. Now on his website, he has the build files for this MCS-48 programmer board. So you can just download the build files and the instructions, send this off to the board house, and fabricate as many of these as you would like to your little heart's delight. And he's taken that one step further because he's also built the adapter for the 8755. So last time I was submitting a board project to the board house, I downloaded his files for the programming shield and also for the 8755, and I just submitted these along with my board project, although I haven't gotten around to building them yet because I have other ways of programming 8755, so it's not really a priority. But I have little doubt that they work as advertised on his website. So that's one option for you if you want to program the 8755. As usual, I found some things that I'll change in the next version. First of all, I will change this little serial port connector. Right now it's just a little 3-pin, has the ground, the transmit, and receive, but I'm going to change that to at least a 4-pin and probably a 6-pin because, some of these little adapters, like this DTEC one, has, in addition to the 5 volts that comes in, it's got the request to send and clear to send. So those are a couple of I/O pins that you could wire up to something else or wire up to maybe an interrupt or something that you want to, who knows what you want to wire them up to. So anyway, I'm going to change this from a 3-pin to probably a 6-pin, bring out the power, and a couple of extra jumpers so that you can connect those to something on board if you want, the request to send and the clear to send. And it is really convenient to use this USB instead of having a barrel connector and a little wall wart sitting around. I'm also going to add mounting holes, and I think that's about it for the changes. It's not meant to be the have-all and be-all. Even if it would be useful, I'm not going to add a bunch of memory. I want to remain pretty faithful to my first wire-wrapped project that I made way back then, and pretty faithful to the original MCS-85 minimum system. But that said, I'm open to suggestions to see what maybe good ideas people have. I do have, the reason I'm not going to add, just a bunch of features to this is because I do have the big brother to this board, which I've been kind of working on in the background, and it's essentially an SDK-85. I just need to get around to building one. I have a bare board set here. I'll give you a sneak peek. It's actually a 2-board set. This is the processor board. It's got a 8085, and then it has a pair of 8755s and a pair of 8155s. It also has a pair of 8185s. So this is going to have 4K of EPROM in the two 8755s. It's going to have 2.5 kilobytes of RAM, since 2 kilobytes in these 8185s and then a 1/4 kilobyte in each of these 8155s. And then it has, a boatload of I/O from all 4 of these support chips. Then I have room over here for a ZIF socket for an additional EPROM, and I'm pretty sure I made that a universal socket, but right now I forget. It says that this was made in week 26, so I've been through a couple of memory refreshes since then. There's a MAX 232 over here and a 9-pin D connector for a serial port. Now I kind of forgot what this chip is over here. I remember it being important because I had to rearrange part of this board. Let me look to see what that was. Okay, yeah, that's another universal site. So this is another EPROM. So we can have either a RAM or a EPROM in this socket right here. So in addition to this board, there is the keypad and display board. It mounts over this, so it's got holes. You can mount standoffs onto it. It has a little notch out of the corner here for the ZIF socket. Has a keypad here for normal cherry keypad for key switches, and then a hex display up here. I guess the differences from the SDK is I've got a few more keys on this. It has the 8279, which is the keypad and display controller. And I think I've got, this is 12 digits of display. Each of these are 4. So I have, a few more digits to display than the SDK-85 can. But with a little bit of porting, because the addresses are different on this because of the extra memory that I have on this. The addresses are different, but for the most part, this should run the SDK, the full SDK monitor. So the base EPROM plus the expansion monitor EPROM on the SDK-85. So this project's something to look forward to if you always wanted an SDK or equivalent, but just haven't got around or haven't found one to buy. So back to this minimum system board. As my usual offer for the first run of new boards, I plan on giving any extras away on a first-come, first-served basis, and the usual conditions that I would hope to get feedback, and that if you want one of these bare boards, that you would at least want it bad enough to pay for the postage. So if you want one of these bare boards, just leave a comment below indicating that you want to join the queue. We'll use the comment order as the queue, and I will send out boards in that order until the boards last. So after you leave a comment, then follow up with an email, and we can get together the addresses and such, and you can PayPal me the postage. In the US, postage is usually under $5 to send one of these. Now, I forget how many of these little Matt Millman Arduino shields and the converter or adapter boards I have made. It would either be 5 or 10 sets. So if you don't have a programmer for the 8755 and you want one of these boards and you want one of these sets, I can also send you a pair of this, the shield and the adapter. But this isn't my board, so these aren't going to be a freebie. You can go out and make these if you want. They're entirely Matt Millman's design, and I'm sure that somebody's selling them on eBay if you want to go look there. But I would like to recoup, the $5 or so that it cost me to have these boards made and shipped over here. So if you want the freebie board, let me know if you want these two, and then for the cost of shipping plus an extra $5, I'll give you these two Matt Millman boards. But as I said, I haven't tried these at all. I can't vouch for them. But I did order some so that I could try them out, and I wanted to test them before I could give a wholehearted recommendation on them. Okay, so that would be the cost of shipping plus an extra $5 if you also want to include these two boards. No guarantees on these boards. Well, no guarantee on this board either. Nothing comes with a guarantee. I think that's it for this video. After I make whatever I'm going to make for the back display, probably a clock, I will make an update video. Rather than a clock, I've also been thinking about, I've been tripping over this. I had it sitting here. Here it is. This was back in about 83, 84, 85. I made this. This is a Digitalker. So this is National Instruments speech synthesis system. So this is the speech synthesizer and some ROM chips that has vocabulary, because this just uses the pre-made vocabulary. But I may put this on the back of that. Make a little Digitalker system. The problem is with the limited vocabulary, it's not really universal. You can't just have it say whatever it sees on the serial port. So I haven't really decided, but if you have an interest in the Digitalker, maybe that will be a future project. So let me know what ideas you might have for the add-on board, if there's something you'd like to see or a better idea than just the clock or the Digitalker. All right, well, thanks for watching. Let me know if you have any thoughts or comments. I will talk with you later. Bye-bye.